Hello, physics students. Let's talk about measurements of length, mass, and time. So as we work through this, we are going to learn how to record data in scientific notation and also use SI metric units. Here's the assessment questions we'll do at the end. And some terms we'll talk about as we work through: measurement, matter, mass, length, surface area, volume, and density. So it's scale, macroscopic, microscopic, temperature, scientific notation, and exponent. And we'll talk about the density equation. And off the top of my head, I think if this appears on the physics reference table, that it probably appears as D equals M divided by V, although I'm fairly certain that on the AP Physics 1 reference table it does appear as rho, a kind of P-ish looking thing here. That's the Greek letter rho equals M divided by V. Alright, so the International System of Units is a system of standards which describe certain amounts of things. So those things are mass, or at least the ones we're talking about right now are mass, length, and time. And they're defined as being a certain amount of, a certain type of atom would be defined as having a mass of 1 kilogram. The length, I believe, is defined by the amount of distance light travels in a certain period of time. And then time is defined, I believe, based on the decay rate of like a radioactive isotope or something like that, if you go look at what the standards are. All right, and in physics and the mechanics part, we're going to have to understand mass, length, and time in order to be able to do that. So, mass is the quantity of matter present, and in common language, you may see it used as, oh, the store had a massive blowout sale. So, they're trying to say large here, not that it has a certain amount of mass in a physics definition. Okay, in common language, when you're saying something like, how long are you going to be in there? The word long could be misinterpreted as time. So if you're asking for how long, what is the length of something? Or if you're asking for time, how much time will it take to fill in the blank? All right, now, usually when we represent time, we mean a quantity of time, whereas you might ask a question like, what time is it right now? We're more likely to ask questions like, how long will it take for something to happen? All right, so each of these quantities has its own SI unit, and here you go. So mass is going to be measured in kilograms, length in meters. Notice the symbols are listed off here, and time in seconds. And here are the other quantities that also are measured in metric units. And we'll get to some of these later. Probably not candelas and moles as much. By the way, you might feel like, well, wait a minute. Temperature is measured in Celsius. Well, yeah, it is, but the Celsius scale can easily be converted to Kelvin. If you're in Celsius, simply add 273 to convert to Kelvin. All right, so what is mass? So rock is matter, gas is matter, and when you stick your hand out of the window of a car, you feel the matter in the air pushing back against you. So mass is an intrinsic property that measures the quantity of matter in an object. And your mass doesn't change even if you go into space. whereas your weight would change. Say that's an extrinsic property. It depends on how much gravity is pulling down on you. So your weight does change if you go into space, or really even if you climb up to the height of a tall mountain. Not enough for you to notice it probably. But yeah, if you go to space or to a different planet, your weight does change. Objects with more mass are more difficult to speed up and slow down. You probably notice that in your everyday life, probably. And just an example, if you try to throw a bowling ball versus a beach ball, you'll notice that it's quite a bit easier to move the beach ball than it is to move the bowling ball. All right, so the concept of inertia has a lot to do with you try to make something move, you try to make something stop. The more massive something is, the more inertia it has. A common example I see frequently is when students move the computer cart, and they don't really take into account the slowing down part of the cart, and it takes just as much effort to slow it down as it does to speed it up. All right, so when we measure mass, we have to have a value and a unit. So, for example, here this object has a mass of 2 kilograms. So the value is 2, the unit is kilograms. Here are some examples of different objects having different masses. So a dime has a mass of about 1 gram, a couple of nickels maybe 10 grams, some steel hardware maybe about 1 kilogram. A rock might also have a mass of about 1 kilogram. A larger quantity of water, because water is less dense than the rock, might also have a mass of 1 kilogram. And then it would take quite a bit of air to add up to a mass of 1 kilogram. So this is showing the use of an electronic balance. You can also use a triple beam balance, or maybe like you've seen a Doppler scale or something. And there's some levers, simple machines kind of stuff going on here in balancing the load. But basically the way that this works is that you adjust the position of the masses on the triple beam balance until the scale is balanced, until this points directly at 0. You'll start doing that with the largest mass, move it over, and until it overbalances, then move it back 1. Repeat that process with the smaller masses until you have it perfectly balanced. Now, to get the final mass of the whatever object, if you have these readings, then you add them up and you arrive at the total mass of whatever object you're measuring. Digital balances are much easier. All right, so let's talk about measuring length. So length is a fundamental quantity. That means it's not combined with any other quantities. So the English system we measure in inches, feet, and yards, while in the metric system centimeters, meters, kilometers, occasionally millimeters for something small. Okay, so the SI base unit for length is in meters. It's basically so the measure of space. All right, and then time is also a fundamental quantity. SI unit is the second. And just a few things that might be useful conversions for you at some point is that a millisecond is 1/1000th of a second. And you also need to know that a minute is 60 seconds, an hour is 60 minutes, or 3,600 seconds. A day is 86,400 seconds. And a year is about 31,579,000 seconds. All right. And then we're going to talk about perhaps the mixed units that come with time, because when you read off of a stopwatch, they're telling you some things that perhaps are not abundantly obvious. So if you want seconds out of this, so the 9.2, well, that's seconds. Then this is 20 minutes, so you have to convert 20 minutes to seconds. Well, that's 20 times 60, so that gives you 1200. And then 2 hours, well, 2 hours times 3600 seconds in an hour gives you 7200, to give you a total of 2 hours, 20 minutes, and 9 seconds, being the same thing as 8,409.2 seconds. So you have to think carefully sometimes when you record values off of a stopwatch. All right, let's see. So there is a interactive equation here converting mixed units. So pull that up and perhaps give that a try with some things, and can work through some of these examples and see how to go from a certain quantity of hours, days, minutes to seconds. All right, now when we deal with measurements, we have an issue of scale. So there are very small things like atoms, and there are very large things like the distance between planets and solar systems and stuff. So it's and then on kind of the human scale, then there's us right here measuring in meters is fairly convenient. So when we talk about scale in physics, things that are macroscopic are generally the things that are big enough for us to kind of see and interact with, and then the microscopic scale gets down into the things that are too small for us to see and interact individually with. You're not going to be able to take a pair of tweezers and grab a single atom or molecule. All right, so the macroscopic scale includes the scale of ordinary life, while the microscopic scale is much smaller, where we're talking about atoms and molecules that make up matter. All right, scientific notation is one way that makes it easier for us to work with large numbers or large range in numbers that we use to describe the physical world. So what we do is we take a coefficient like 4.3 and then multiply it by a power of 10. And when you do that, if you have a larger power of 10, then the number is progressively larger. And as you get a more negative power of 10, like let's say we did -3, then that would be a or a smaller quantity or smaller number. All right, so just for thought here, power of 10, 10 to the 1 would be just 10. 10 to the 2 would be 100. 10 squared, 10 times 10 is 100. 10 to the third power, 10 times 10 times 10 gives you 1,000. 10 to the fourth gives you 10,000, and you can keep going like that. Now, for numbers that are small, the exponents become increasingly negative. So a negative exponent means that essentially you're putting this quantity in the denominator. So this would be like doing 1.5 divided by 10 to the third power. So 1.5 divided by 1,000, and that would be equivalent to 0.0015. You may have also talked about moving the decimal place. So if it's a small number, you move the decimal, or negative exponent, you move the decimal place to the left, and that makes this into a number less than 1. All right, so I'm going to pause there, and we'll come up and finish the rest of this in a second video.